Whenever paradoxes show up in math, I get uncomfortable. I don't like it when things seem to be two ways at once, and those two ways contradict each other. In general, okay, tons of things in life are ambiguous. But not math, right? Paradoxes are excellent teachers, though. They encourage us to take a step back and think about what the symbols really mean. And by resolving them, we upgrade our logical flaw detectors and get a deeper understanding of the math. It also just feels good to dig in and figure out where some argument that at first seems so solid is going wrong. The paradox I want to talk about in this video is one that comes from physics, in particular the study of electrostatics. If you're not familiar, the whole program of electrostatics can basically be summed up in one question. Given a collection of point charges distributed in space, what is the total electric field produced everywhere? The electric field is a vector function of position, so we can think of it as an arrow associated with every point in space. Its magnitude and direction depend on where the point charges are, their strengths, and whether they're positive or negative. Here we're also thinking of them as being stuck where they are. That's where the static part comes from. Now, there's another quantity we often talk about called the electric potential. This is a scalar field filling space, and it's something you can also derive from the distribution of charges. These two fields are really two sides of the same coin, though. The electric field is equal to the negative gradient of the potential. So if you think about the potential as analogous to a landscape, positive charges sit at the tops of mountain peaks, negative charges sit at the bottom of pointy valleys, and the electric field everywhere on the landscape always points directly down the slope, with magnitude determined by the steepness of the slope. In Cartesian coordinates, for example, that means that the components of E are just the partial derivatives of the potential along each axis direction. The reason we care about the potential in the first place is that unlike the electric field, where you have three functions to calculate, the potential is only one. And in real-life situations, it's often more convenient to compute the potential first, and then just take the gradient if you want the electric field. So that's all we need as background, and now comes our problem. Suppose we have a straight piece of conductive wire. We put some charge on it, and we spread it out evenly. Positive or negative, it won't really matter in the end, but just for concreteness, let's say it's positive. The question is, what electric field and what potential field does the wire produce, and are they consistent with each other? What I want to show you is that if you do what looks like perfectly reasonable math, you run into a contradiction. But by looking closer, we'll figure out what's going wrong and how to fix it, and also gain what I think are some surprising insights in the process. Before we even start though, let's actually make things even simpler and let the wire be infinitely long. That might not seem like much of a simplification, but you'll see why it helps when we start deriving things. Okay, let's first try to work out the electric field. We can build things up here by remembering that the field produced by a single point charge in empty space is proportional to the amount of charge q divided by the distance to the charge squared. If the charge is positive, the field points away from it. If it's negative, the field points towards it. The factor k is just a constant that helps the units come out right. Its exact value depends on, for example, whether you're measuring distance in meters or miles. The corresponding potential is kq over r, and it has a nice spherically symmetric gradient. I started with a point charge because we can think of our uniformly charged wire as essentially a long string of identical point charges. To get the electric field at some point in space, we can just add up all the contributions from each little point on the wire. Our line of charges is infinite though, meaning the total charge of the wire is as well. So we won't be able to write E in terms of some total charge, but we can talk about a finite charge density. Let's call it lambda. This is a constant property of the wire that says that if we take any piece of the wire with length delta x, say, the amount of charge in that piece is just lambda times delta x. And an infinitesimal bit of the wire dx contains an infinitesimal charge dq, which in turn produces an infinitesimal electric field dE, at the point here, for example. Let's go ahead and plug this in. To get the total field produced at that point by the whole wire, we just integrate over the whole length of the wire, which I'm thinking of as lying along the x-axis. Alright, so we've translated our physics problem into a concrete math problem, and at this point we have a few options. One is to just forge ahead directly. Start writing everything in the integral in terms of x, and then just try to crunch our way to the solution. A better approach, though, is to first think about what we expect the answer to look like. Without doing any calculations, we can say, for example, that the electric field can't have any component in the x direction, that is, along the wire. It can only point along the direction perpendicular to the wire, and for the same distance, the magnitude has to be constant. Notice how this wouldn't be true if the wire weren't infinitely long. There's also rotational symmetry. The magnitude is constant on circles like this in the plane perpendicular to the wire. Given all this symmetry, the problem is pretty much screaming at us to use Gauss's law. And we absolutely should. I don't want to get too distracted by details though, and lose sight of the larger point, which is that we do in fact get a perfectly reasonable answer for the electric field. So I hope you'll forgive me, but I've decided to just show the answer now, and make a follow-up video that walks through how to use Gauss's law here. We can at least check that it's well behaved though. It's proportional to the charge density, that seems good, and inversely proportional to distance. Also good. So that's one field down, and we'll just keep this over here for later. Now, let's compute the potential from first principles. We can basically use the same strategy as before. Think about the contribution to the potential due to an infinitesimal piece of the wire. This is k lambda dx over r. Then taking the origin to be at the center, x is this distance, and Pythagoras gives us the hypotenuse. Let's just plug it in. And like for the electric field, we integrate this expression over the whole x-axis to get the total potential. Unfortunately, we don't have something like Gauss's law for the potential, so we just have to do it the old-fashioned way. Now I want to point out that v should only be a function of y, which makes sense because the wire is infinite, and y is a constant as far as the integral is concerned. We'll do a little simplification here and change the variable to u, where u is x over y, and we might as well pull the constant lambda out front too while we're at it. And if you're anything like me, you can do integrals like this in your sleep. Just kidding. That's not good. I guess the first sign of trouble we could have noticed was that this whole integral has to evaluate to just a constant, meaning v doesn't actually depend on y. The corresponding electric field is just zero then, since it's the derivative of a constant. But it's actually worse than that. This integral apparently diverges. It's in some sense an infinite constant. What are we supposed to do with that? So we found the contradiction I was talking about. E is fine, but V's got big problems. Okay, let's back up a second and think about the physics. The electric field we got seems reasonable. If it points down the slope like it's supposed to, the potential should look something like this, a gradient perpendicular to the wire everywhere, and definitely not infinity. Maybe it's a problem with these infinite limits. Just for a second, let's try chopping off the integral at some finite value, say x equals plus and minus L over 2. Since we changed our integration variable to u, the limits become plus or minus L over 2y. So let's try this again. This seems promising. We at least get a finite answer now. The inverse hyperbolic sine function might look a little scary, but it's really just a natural logarithm in disguise. In our case, the argument is L over 2y, so we can write the potential like this, where I'm just using a to make it look a bit cleaner. Remember what we're really interested in though, is the limit when L becomes huge compared to y, meaning a goes to infinity. A squared then completely swamps the 1, and the stuff in parentheses just acts like 2a. Putting back our original variables, we have that v equals 2k lambda times the natural log of L over y. This seems like progress. What have we done though? Let's take the gradient and see. Since our problem is effectively one-dimensional, the gradient is just the derivative with respect to y. The first term just gives 1 over y, and the derivative of a constant is 0. There we go. We found a function whose negative gradient is the electric field. It's kind of weird though, right? that arbitrary cutoff length is still lingering in the potential. No matter what value it has, the electric field doesn't depend on it. We shouldn't be too worried though. The potential is just a mathematical convenience anyway. At the end of the day, the physically observable quantity, meaning the one we really care about, is the electric field. And if you're familiar with the physics, you'll recognize this as a manifestation of the inherent ambiguity in the definition of potential. It's only differences in potential that have physical meaning, and we're free to set the reference point wherever we want. So, crisis averted, and we can better see what's going on now. We were able to fix the infinite potential by bringing an arbitrary length scale into the problem and hiding it inside a logarithm. And with the benefit of hindsight, we can get at the answer another way from more general arguments. Given that the electric field looks like this, the potential must have the form 2k lambda times some function of y. And we might be tempted to say, okay, well, I know the derivative of natural log y is 1 over y, so that's the answer. But that can't be right because the units don't work out. The units of potential are whatever k times lambda has. In the usual SI system, that's volts. And as the derivative of potential, the electric field has the units the potential has divided by length, because taking the derivative with respect to distance puts 1 extra unit of length in the denominator. That means we need f to be unitless, so that e gets the right 1 over length when we take its derivative. We can make that happen by always dividing y by a fixed length scale wherever it appears. The trick, though, is that e can't depend on that length scale. It has to disappear when we take the derivative. In other words, we need a function that turns division into subtraction. That's a job only a logarithm can do. The last little thing to fix is that since e is minus grad v, we need to put y in the denominator. And we've got it. This last argument was pretty subtle, and it certainly wasn't a rigorous proof. But this style of thinking can be really helpful when you run into trouble with physics problems, and you can get better at it with practice. I like this problem because it reminds me that logs have these powerful and unique properties, but it also helps me understand the relationship between math and physics better. Unlike the flawed proof that 1 equals 2, which is an exercise in pure mathematical logic, our solution came from thinking about a physical situation and reasoning about math, but with 1 foot anchored in reality. We had to bring in some physical intuition to the problem. If I was only interested in the math and someone gave me this integral to solve, I probably would have just said, well, it's infinity. What more do you want? But because this answer didn't make physical sense, we knew there was more work to do. Math on its own can live happily untethered to any consideration of the real world, and it can be beautiful for exactly that reason. But it's also the language we use to describe the physical world. And when we use it for that purpose, the symbols take on meaning within a certain context. In my experience, getting stuck in physics problems almost always comes down to forgetting that context. I hope you enjoyed this video and that you learned something new. Thanks for watching.